Good morning. We are now dealing with the earth dams and spillways in Unit 3, Water Resources Engineering-2. To have a simple recap about what we have discussed in the previous class on earth dams, you have seen what is an earth dam, what is the importance of the earth dam, types of earth dams, causes of failures we have seen in the last class. Today, we'll be concentrating on criteria for safe design of earth dam, seepage through the earth dam, and the graphical method. So forget about all the numericals, but if you look at the earth dam section, it may be having the slopes on the upstream side, the slope on the downstream side also. Usually, the height of the dam will not be much. Earth dam's height will not be much, maybe about 40-45 meters. In this case, you may see the height of the earth dam is about 20 meters. About 20 meters. This is only indicative figure, nothing connected with the theory of the earth dam, but this has been taken from some of the problem from Punmi and all to provide you how the section of earth dam looks like. So there will be top width and upstream slope, downstream slope, followed by at the toe portion, there will be a filter provided. So this filter is provided in certain specific types of earth dams. So to have a recap of what we have discussed in the earlier class on earth dams is that what is the importance of earth dam we have seen. So what are the advantages with the earth dam? First of all, earth dam is constructed with the locally available earthen material. So it will be very economical, is the biggest advantage with the earth dam. We don't require skilled manpower is another advantage with the earth dam. But at the same time, there are certain challenges also for the earth dam. The challenge that would be there in the earth dams is because you are using only an earthen material, there is always a possibility that seepage may take place. So how to arrest the seepage, how to minimize the seepage, how to control the seepage, and how to see that the dam is safe against the seepage is the biggest challenge. So we have seen the types of earth dams like rolled fill dam and hydraulic fill dam. And in the rolled fill dam, once again, you have like homogeneous embankment type, that means a single kind of material. Zoned embankment type, more than one type of material may be used in the earth dam. Then diaphragm type embankment will be there, where you have a thin diaphragm of impermeable material provided to check the seepage through the body of the dam. The second category is the hydraulic fill method, where the slurry will be prepared and the same thing will be directly transported by the mechanical means. In the case of a rolled fill dam, the other material will be laid and then it will be sprinkled with water and then it will be compacted. Whereas in the case of a hydraulic fill dam, it will be different, that the water will be mixed at the in situ where the soil is available and the same thing will be transported and poured at the dam section. And also we have seen about the causes of failures of the earth dam. Basically, there are three types of failures, like hydraulic failure, seepage failure, and structural failure. The 40%, 30%, 30% gives you an indication that the previous history of the earth dam failures, about 40% of the earth dams fail because of the hydraulic failure, about 30% fail because of seepage failures, and another 30% because of structural failure. Under the hydraulic failure, we had seen like overtopping is one biggest problem, where you have the maximum water level more than the top level of the dam. That means the water overflows or over the body of the dam, may be resulting in failure of the dam is one hydraulic failure. And then wave erosion is another thing, toe erosion is another thing, and gullying because of high intensity rainfalls which are directly taking place, the rainfall is directly falling onto the body of the dam, may be resulting in gullies and then failure of the dam. So these are the hydraulic failures. Under hydraulic failure, you have overtopping, wave erosion, toe erosion, and gullying. And the second type of failure is the seepage failure. About 30% of the failures may be because of the 30% of the dam failures may be because of the seepage failure. Piping and sloughing. What is piping? It is a progressive erosion of the concentrated leak. So the water flows in the form of a pipe from upstream to the downstream through the body of the dam, may be resulting in the failure of the earth dam. Sloughing is that under full reservoir level condition, downstream toe is in saturated position and it gets eroded and it is called sloughing. This is also another type of failure. Then The structural failure, it is about contributing to over 30% of the failure of the total earth dams. Upstream and downstream slope failures due to pore pressure, and upstream slope failure due to sudden drawdown, downstream slope failure due to the full reservoir levels and conditions related to that, and foundation slide, earthquake failure, slope protection failure, failure due to water soluble material which is available in the composition of the dam. All this may be leading to the structural failure of the dams. So in all these types of failures, what precautions are to be taken to see that, to safeguard the dam against these type of hydraulic or seepage or structural failures also we discussed in the last class. In brief, this is all the points that we have discussed in the previous class. Today, we will be taking up the criteria for safe design of the earth dam, seepage through the earth dam, and a graphical method for arriving at the top flow line, phreatic line. Okay. So criteria for safe design of the earth dam. So what is the criteria to be followed to design a safe earth dam? This is a condition. Embankment must be safe against overtopping during inflow floods. We have seen the type of failure in the earlier case also. In the earlier, when we were discussing about the causes of failures, overtopping is one biggest problem. If the flood is not sufficiently estimated into the reservoir, and already earth dams have got a limitation that you can't have very higher heights of earth dams, maybe limited to very minimal height of about 40-50 meters only. So what will happen is that if more water is coming into the reservoir, and if the flood is not appropriately estimated, that means you underestimated a flood. So maybe 2 lakh cusecs of water is coming, you have estimated and you have designed, and the reservoir capacity and the height of the dam accordingly. But all of a sudden there may be 3 lakh cusecs of water which may be joining the reservoir, which indicates that huge flood inflow is there into the reservoir, resulting in the rise of the full reservoir level and hence the overtopping. That means the water flows over the body of the dam, maybe leading to the failure of the earth dam. So the criteria for the safe design is that the embankment, the dam section what you are taking must be safe against this overtopping during the inflow flood. It must have sufficient freeboard. Once again, related to this only, like the freeboard that is provided must be sufficient enough to take care of the wave erosion, to take care of the overtopping. Seepage line must be well within the downstream phase so that there will be no sliding of slope. When the water is flowing through the body of the dam, as we indicated in the causes of failures also, that the top flow line or the phreatic line or the seepage line must be well within the downstream phase so that there will not be any problem of sliding. Sliding failure is something like the toe portion gets eroded because of the seepage. So seepage flow must be controlled so that no erosion takes place, and there should be no opportunity for the free passage of water from upstream to the downstream side. This is another criteria. There should be no opportunity for the free passage. If the water starts flowing freely from upstream to the downstream through the body of the dam, there is a possibility of the failure of the dam in terms of the piping, So seepage failures. So portion of the dam downstream of the impervious core must be properly drained, and safe design of the side slopes also. The side slopes we have seen, unlike gravity dam, for the earth dam, you have upstream slope as well as the downstream slope. That's why the base width also will be so big. Base width will be so big as compared to the gravity dams. So we need to see that the total slopes, both side, upstream side and the downstream side also must be properly designed. The side slopes must be properly designed, and in any case there should not be any slope failure for the embankment. In any case, there should not be any slope failure for the embankment. Similarly, the downstream slope must be safe under the full reservoir condition also. Upstream slope must be safe under the rapid drawdowns. The condition of rapid drawdown will be like you are withdrawing the water through the sluice gates, and also you may be allowing the water to flow from upstream to downstream during the flood periods through the spillway. In such cases, there is a possibility that the water level, the full reservoir level, may be moving down, slowing very, very fast. It is moving down. So under this rapid drawdown condition also, upstream slope must be safe. Slopes must be flat enough. We have seen in the figure also. Must be earthquake resistant, and no erosion due to waves should be there. If more and more waves are coming up, there is a possibility that the upstream slope may be eroded, upstream slope may be destroyed. So this is the criteria for the safe design. One by one, let us try to see. Embankment must be safe against overtopping and must have sufficient freeboard. You can see in the figure that you have the sufficient freeboard. So this is the freeboard from the top to the top water level to the top of the dam. So this level difference is the freeboard, and you should have sufficient freeboard that is provided. And this embankment must be safe against overtopping. Seepage line must be well within the downstream phase so that no sliding of the slope takes place. So the seepage line or the top flow line or the phreatic line, by providing a filter, this seepage line is seen to it that it will not cut the downstream phase. So seepage flow must be controlled so that no erosion takes place, and there should be no opportunity for the free passage of water from upstream to downstream portion. If the filter is not provided, there is every possibility that the water may be flowing from upstream to downstream portion, So to avoid that, a filter will be provided at the toe portion, so that the seepage line will not cut the downstream phase, but it will cut the base at some point like this. And portion of the downstream of the impervious core must be properly drained. So you should have a proper drainage by providing the gravels here. Say this is the toe drain. This is the toe drain which will be provided. So safe design of the side slopes. You should have sufficient side slopes here. Downstream slope must be safe under the full reservoir, and upstream slope must be safe under the rapid drawdown condition. Suddenly, if the water level is moving down because the water is being withdrawn from the reservoir, the upstream slope failure may take place. So to avoid that, we need to have a safe criteria for the design to see that under the drawdown condition also the upstream and downstream slopes must be safe. And slopes must be flat enough. You see here. So flat slopes will be there. This type of flat slope is not required in the case of a gravity dam, because you're using either masonry or concrete. You can have a vertical face also, but here no such possibility of having a vertical face. Okay, so that is about the criteria for the safe design of the earth dam. Now, filter. We have been using this term filter. So at the downstream portion, near the downstream toe, we are providing a filter. Because the filter is provided, when the water is passing through in the form of a seepage from upstream to the downstream portion, it will not cut the downstream face of the dam, and hence filters are necessary for any of the earth dam. So filter zones are invariably provided in all the earth dams. They are constructed of material more pervious than the embankment soil. Provision of the filter zone at the downstream serves to reduce the pore water pressure in the downstream portion, so that it increases the stability. Also, it checks the piping by checking migration of the particles. Three types of drains will be there. The first one is the toe drain. That means a drainage is provided at the toe portion of the dam. So if this is the embankment or the section of a earth dam, at this toe portion, more boulders, bigger size boulders compared to the material used for the earth dam is provided. This is called a toe drain. So you can see at the construction of the toe drain also. You may see here, of course, the figures are only indicative, like 25 centimeters, 15 centimeters, 30 centimeters thickness are only indicative. But you can see here the composition of this drain, how this has been provided. Say a rock toe will be provided here, and surrounding this rock toe, you have a gravel, then coarse sand, then fine sand, followed by the material which is used for the soil which is used for the embankment. So this is how a toe drain will be provided. You have the rock toe followed by enclosed with the gravel, enclosed with the coarse sand, enclosed with the fine sand, followed by the soil. So this is how toe drain will be provided. The second category is the horizontal blanket which is provided. So for a dam section, the horizontal blanket is the horizontal filter which is provided like this from the toe portion up to certain portion in the base, You can see here the composition of this horizontal drain or horizontal filter, horizontal blanket, what we call. You can see here more coarser material at the bottom portion, finer portion at the top for this horizontal filter. Because this horizontal drainage system or a filter is provided here, the seepage line, the top flow line which is starting here, is getting diverted and joining into this filter. If this filter is not provided, then what will happen? This seepage line may cut the downstream face of the dam, leading to the failure of the earth dam. Third category is providing a chimney drain. See, if this is the section of a dam, a chimney drain may be provided like this. Instead of only leaving at the horizontal blanket, you have certain vertical portion also for it, then it is called a chimney drain. It is called a chimney drain. For a typical section of an earth dam, a chimney drain may be provided starting from the toe portion of the dam, extends up to certain portion where the core, central impervious core is provided, and it touches the body of the central impervious core till the top of it, till the top of the core. So this is what is called the chimney drain. This is the chimney drain. So it is something like L shape. The bottom will be directly from the toe, just like a horizontal drainage filter, and the vertical portion will be connecting to the central core of the dam. If the central core is not there, central impervious core is not there like this, then you may have a simple chimney type of thing like this. You will have a simple chimney type of thing like this. So there are three types that we have seen. One is the toe filter, and the other is the horizontal filter, and one more is the chimney drain filter. So how to choose this filter criteria? The dimensions on permeability of the filter drain must be chosen in such a way that the drainage system can carry away the anticipated flow with the safety. This is how the size of the filter and the filter provision is required for a dam. The main purpose of providing a filter is to see that the flow which is taking place through the body of the dam must be collected through into this filter and must be safely disposed to the downstream portion. Multi-layered filter is generally provided, as we have already seen, like coarser, fine sand, and then gravel, one after the other will be provided. This is called multi-layered filter, is generally provided, in which each subsequent layer becomes increasingly coarser than the previous one. So this type of filter is called inverted or reverse filter. According to Terjigi, the filter material should fulfill the criteria, something like D15 of the filter material by D85 of the base material must be less than 4 to 5, also must be less than D15 of filter material by D15 of the base material. So this criteria given by Terjigi has been further modified, like D15 of filter material divided by D15 of base material must be equal to 5 to 40, condition 1, provided that the filter does not contain more than 5% of the material finer than 0.07 micromillimeters, 200 sieve number. So the requirement stated above must be satisfied between any two adjacent layers of the filter. So what is this D15? That is the particle size of the diameter of the coarser material at which 15% of the material becomes finer. Similarly, number 2, second criteria is D15 of the filter material divided by D85 of the base material is equal to 5 or less, and D85 of the filter material by maximum opening of the pipe drain must be equal to 2 or more, that means greater than or equal to 2. The grain size curve of the filter should be roughly parallel to the base material. That's how all these embankments, the design of embankment, slope failures of the embankment, stability of slopes, everything will be studied in the foundation engineering subject more clearly. But anyway, we'll be taking up the hydraulic design part. Seepage through the earth dam. Filter criteria we have seen. Criteria for the safe design of the earth dam, followed by filter criteria we have seen. Now, seepage through the earth dam. We have been indicating this word seepage. This is the biggest challenge for the earth dam, because in spite of the compaction being done in the form of layers in the case of road fill dam or maybe a hydraulic fill dam, seepage is inevitable through the earth dams. Seepage is inevitable through the earth dam. On the upstream side, water will be there in the full reservoir condition, and the downstream side, the water may be there up to tailwater, sometimes no tailwater also would be there. Because the water is getting stored on the upstream side, through the connected pore spaces of this dam section, there is a possibility that the water may be flowing, which is known as the seepage flow. Let us see how the seepage would occur in the gravity dam. Yeah, this video mainly depicts about the two issues, a dike model, the simulated study with the different runs, how the seepage line would be through an earth dam section. Two cases have been taken. In the first case, you have a earthen embankment directly, and how the seepage is taking place is shown through an arrow, movement of the arrow, how the flow is taking place. Second part is that by providing a small central impervious core, how the seepage line is getting changed. So these are the two things which have been shown in the previous video. So this video mainly is providing us the details of how the movement of the flow of water within the body of the dam, that is a seepage line, phreatic line, and its position has been shown. A more in detail study now we will see seepage through the earth dam and how to compute the rate of seepage from this flow net analysis. We have already studied about the flow net in our second year fluid mechanics subject. You have the combination of it is a network of the streamlines as well as equipotential lines. This definition we know. Let us not bother even if you forget about that, but we try to define what is flow net and we try to proceed also. It is a network of equipotential lines as well as the flow lines, also called the streamlines, and this is what is called the flow net. There are certain assumptions which are made for this flow net analysis. It is first of all, we have taken up a two-dimensional flow. Okay, so the portion between two successive flow lines is called the flow channel, and the portion enclosed between between flow and equipotential lines is called a field. Field and channel. Flow net, field and channel. You can see here how the grid is formed. So these are all the streamlines. These horizontal lines are near horizontal lines are the streamlines, and near vertical curves are called the equipotential lines. You have the flow line also called the streamline, and you have the equipotential lines. So the grid which is formed with the combination of flow lines as well as the equipotential lines is called the flow net. So in this flow net, you can see what is a channel and what is a field. Two things are defined here. What is a channel and what is a field. Portion between two successive streamlines is called channel, flow channel. So this is one streamline. This is another streamline. The flow taking place between these two streamlines is called the flow channel. You have one more streamline here, one more channel. So delta Q may be the rate of seepage through this. Another delta Q may be the rate of seepage in between these two streamlines, and this is the flow channel. And through this flow channel, you may have another delta Q. Okay. So if Q is the total seepage taking place through this, sigma delta Q must be taken. So sum of all the discharges flowing through these independent flow channels will be equal to the total seepage flow. So total seepage flow. Then one more definition that is given here is the portion enclosed between the flow and the equipotential lines is called the field. So this is the flow line and this is the equipotential line. In between these two is a field. So the hatched portion here is a field, maybe approximately square. But however, if there is any difference, B and L, the dimension, the size of this field. B and L be the width and length of the field, and delta H is the head drop through the field. When the flow is taking place, there is a drop in head. So from this portion to this portion, from this portion to this portion, delta H is the drop, head drop, and delta Q is the discharge, as we have seen, through a given flow channel. So this is the discharge passing through the flow channel. H is the total head causing flow, and Y is the difference between upstream and downstream heads. So simple Darcy's law, if you apply V is equal to K into I, or the discharge delta Q will be equal to V into A, velocity into area, or K into I into A, where K and I, we know very well A, the area. If you take unit thickness, it will be B into 1. It will be B into 1. So hydraulic gradient I will be delta H is the drop in pressure head, as we have seen. So delta H divided by over a length of L, over a length of L. So the hydraulic gradient will be delta H by L. K, the permeability of the soil or the embankment material. Permeability of the embankment material. So from this point to this point over a length of L, if there is a drop in pressure of delta H, then delta H divided by L will give you the hydraulic gradient I. So K into delta H by L into B into 1, because you are taking only 1 unit thickness for a 2-dimensional flow. So using this Darcy's formula, V is equal to K into I, the discharge passing through the flow channel delta Q, the discharge passing through the each flow channel delta Q will be equal to K into I into A, or K into delta H by L into B into 1. If ND is the total number of potential drops in the complete flow net, then delta H will be equal to total H, total divided by total H, which is causing the flow, total head, which is causing the flow, divided by ND is the potential drops. What is this potential drop? Maybe from one potential line to the other potential line, there is a head drop of delta H. Once again, from here to here, another head drop of delta H. From this point to this point, another delta H is the head drop. So if such potential drops are ND, then delta H will be equal to H by N into, H by ND, H by ND, and N suffix D, N suffix D, ND, the total number of potential drops. Then delta Q will be equal to K into H by ND, delta H will be equal to H by ND into B into L divided, B into 1 divided by L. The total discharge, this is all the discharge delta Q passing through each flow channel. If there are several flow channels, then the algebraic sum of all these flows, the seepages through this will be equal to the total discharge. So Q will be equal to sigma into delta Q. So K into H by N into B by L into NF, the number of flow channels which are available. Number of flow channels which are available. So in the figure you can see this is one flow channel, this is one flow channel, this is another flow channel. So between two successive streamlines, it is called the flow channel. it is called the flow channel. So NF is the total number of flow channels. Then the discharge Q will be equal to K into H into B by L into NF by ND. What is B and L? B and L are the dimensions of the field that we have considered. Usually, it will be approximately square. So, if B and L are approximately equal, then Q will be equal to KH into NF by ND. Valid for isotropic soils, where K you are taking the permeability. If you take anisotropic, where Kx will be equal to Ky. If you take anisotropic soil, the K must be replaced by the equivalent value of the permeability, something like square root of Kx into Ky. If Kx is equal to Ky for isotropic soil, so the discharge or the rate of seepage through the flow net would be equal to Kh into NF by ND. So what is required now is that the permeability of the embankment material and the total head causing flow and the number of potential drops and the number of flow channels. If these things are known, we will be able to estimate the seepage rate through the embankment, through the earth dam. Phreatic line in the earth dams. How the phreatic line, the top flow line, seepage line would be. Let us start from the definition. It is the line within the dam section below which there are positive hydrostatic pressures in the dam. This is what is the phreatic line. You can see here in the figure, this is the top flow line, also called the phreatic line or seepage line, which will be separating the saturated portion and unsaturated portion of the earthen embankment. Saturated portion and unsaturated portion. So this is the top flow line, which is called the phreatic line. So there will be positive hydrostatic pressures below this line. So by definition, phreatic line is defined as the line within the dam section below which there are positive hydrostatic pressures in the dam. So to look at the shape of this phreatic line, the top flow line, which is separating the saturated and unsaturated zones, you have several procedures how to demarcate this phreatic line. Consider the homogeneous earth dam with a filter provided. Homogeneous earth dam with a filter provided. Then this is the approximate shape of the phreatic line. Suppose you have a chimney drain which is provided here. This is a horizontal drain which is provided. If a chimney drain is provided, then the location of the phreatic line would be like this. This is the location of the phreatic line. So a graphical method which is given by Casagrande about locating the phreatic line in an earth dam section, let us discuss. He assumed the phreatic line to be a base parabola with its focus at F, starting point of the filter. This is what the assumption which has been made by Casagrande. So earth dam section is shown here. This is the earth dam section, and a horizontal filter is provided from the toe. So the location of the horizontal filter is FE. FE is the location of the horizontal filter. So he assumed that the phreatic line, this is the phreatic line. This phreatic line is a base parabola with its focus at F. Where is F? F is the starting point of the filter. Starting point of the filter. F is the filter and F is the starting point of the filter. So the focus of this base parabola is assumed to be at the starting point of the filter. So if you try to understand the section, the cross section of an earth dam, you'll be able to look into the graphical method with several step-by-step procedure. I'm sure you must have studied this topic also in your soil mechanics or geotechnical engineering while you are looking at the stability of slopes. However, we repeat because it is there in our syllabus. We repeat again. So this is the earth dam section. So the top width is provided here, and this is FRL, the full reservoir level. This is the full reservoir level. So you can see here AB is the upstream slope of the earth dam. Upstream slope of the earth dam. What is point C here? Point C is taken from point B, measured for a distance of 0.3 L. What is L? In the figure, this is the L, the reservoir. If you take the slope AB, for this slope AB, if you take a horizontal projection, then its length will be L. So 0.3 L, you will get the point C, which is considered to be the starting point of this base parabola. Starting point of the base parabola. Where is it ending? It is moving with the focus of F. The base parabola may be moving with these dotted lines. You can see the dotted lines from C, and this is the base parabola, also the seepage line. Also the seepage line. Further, what else are given on this seepage line or base parabola? Any point P, if you take, the ordinates of the P will be Pxy, where X is the distance measured horizontally from the focus F. From the focus F. Similarly, the vertical distance is Y. Vertical distance is Y. So with F as the focus and C is the point at a distance of 0.3 L measured from point B on a line which is a horizontal projection of the slope AB. Horizontal projection of the slope AB. So let us see one by one what is this. So the prediction of the phreatic line is necessary, of course, to ensure that it will not intersect the downstream phase. We have already seen what are the problems when it is intersecting the downstream phase. There is a possibility of the failure of that. To carry out the stability analysis for the of the downstream phase, whether the embankment is safe or not, and to estimate the seepage flow taking place through the dam. So for this, we need to identify the phreatic line in a dam. The graphical procedure for locating the phreatic line in earth dam is given here. The same figure I have repeated here for your clear understanding. AB is the upstream phase. AB is the upstream phase. Let its horizontal projection be L. So AB is the upstream phase and the horizontal projection in the figure is shown L. On the water surface, measure the distance PC will be equal to 0.3 L. So BC is the distance 0.3 L. Then the point C is the starting point of the base parabola. Starting point of the base parabola is C. To look at the position of the directrix in the parabola, point C as center and CF as the radius, draw an arc to cut the horizontal line through CB in D. So we are now trying to look at the position of the directrix in the parabola. So point C as a center, CF as a radius. This is the point, center point C, and F is here. So CF as a radius, draw a curve. Draw a curve. So this is the curve. So this curve is cutting the extended line of BC, extended line of CB at point D. At point D. Okay. So you are getting now the point D by taking C as a center, CF as the radius, draw a curve. So this curve cuts the horizontal line of BC at point D. So draw a vertical tangent to the curve FD at D. So at this point D, draw a vertical tangent to this curve. So evidently CD will be equal to CF and DH will be the directrix. DH will be the direct. This is point D and DH will be the directrix. So the last point G on the parabola will lie midway between the values of F and the points of F and H. So F is the focus for this base parabola, and H is from the directrix. You have got the point H, and you can see here between this F and H, both are on the filter only. Both are on the filter. The midpoint of F and H is equal to G. Midpoint of F and H is G. So the midpoint of F and H is G, and this is the last point of the base parabola. Now you have got the point C, the starting point of the base parabola, at point 3L from B, and G, the midpoint of F and H is the G is the last point of the base parabola. You have got the starting point, you have got the last point. In order to look at the intermediate points on this parabola, we use the principle that its distances from the focus and the directrix must be equal. So if we take any point P, we will be making use of the simple principle. The distances from focus and the directrix must be equal. For example, to look at any point P, draw vertical line QP at any distance X from F. Measure QH with F as the center and QH as radius, draw an arc to cut the vertical line through Q in P. So this is the point P. To identify this point P, what you are doing? You are drawing a vertical line QP. At point P, you are drawing a vertical line. So you have got QP now, which is at a distance of X from the focus F. At a distance of X from the focus F. Measure the value of QH. Measure the value of QH. Then with the F as a center and QH as the radius, draw an arc. Draw an arc. So this arc will cut the vertical line through this Q at point P. That's how you are getting the point P. Similarly, several points along the base parabola can be obtained, and you can join all the points to get the parabola. And of course, we need to make certain corrections for this base parabola. We have got the base parabola, but this base parabola is not directly the seepage line. There are corrections which are required to be done. What is this correction which is required to be done? What is the correction that is to be done? At the entry point, point C is the starting point of the base parabola, but point C is directly in the reservoir. So where is the flow in the reservoir? There is no soil at all to have the seepage. By definition, seepage is the flow of water through the body of the dam. There is no body of the dam at point C. At point C. So though the base parabola is starting from C, but the seepage line starts only from B. So you should have a smooth curve. You should have a smooth curve from B to join to this base parabola, so that you will be getting the exact curve of the seepage line. So to find the equation for this phreatic line, consider P, any point on this base parabola, as Pxy with respect to the focus F. So from the property of the parabola, as you have seen, both the distances must be same. So PF must be equal to QH. PF must be equal to QH. Accordingly, you measure what is PF and what is QH. So this is the diagonal. PF is the diagonal. So for this PF, the diagonal, P is located at a distance of XY. So PXY is the point. So square root of x square plus y square will be equal to the diagonal PF. The diagonal PF. So square root of x square plus y square will be PF. And on the right hand side, you have QH. So QF plus FH. QF plus FH. QF already is, we have seen X, and S is the focal distance, which is FH. So X plus S. So you got now square root of x square plus y square must be equal to X plus S. Three things are here. What is X, what is Y, and what is S? S is the distance between the focal point F and the H. The H is from the directrix. So the distance FH is S. The distance FH is S, which is on the filter. And X and Y, the coordinates for the point P, which is considered on the base parabola. So PF will be equal to QH, or square root of x square plus y square must be equal to X plus S. So taking square on both the sides, you will be getting square root of x square plus y square becomes x square plus y square. And on the left hand side, you have X plus S whole square, x square plus s square plus 2x. Yes. Your x square on the left hand side, your x square on the right hand side getting cancelled. Y square is equal to s square plus 2x. Yes. Or x will be equal to y square minus s square divided by 2s. So this is the equation of the base parabola. This equation will be used for finding the values for several points of y. What is the corresponding point x can be found. So if you have the values of x, y, all these points, line joining all these points gives you the smooth value of the parabola, smooth curve for the parabola. So this is the equation for the base parabola. And to get the expression for the discharge Q, we have a simple expression based on the value like V is equal to K into I. So from there, the discharge Q will be equal to K into I into A, and K into I, the hydraulic gradient over by x, into A for the unit thickness, it is Y into 1. So making use of that, y is equal to square root of, making use of this equation, y is equal to square root of 2xs plus s square. Dou y by dou x will be this value. So substituting dou y by dou x in this equation, you have square root of 2xs plus s square, square root of 2xs plus s square, both in numerator and denominator gets cancelled, and your Q, the discharge, that is seepage, rate of seepage through the body, will be equal to K into S. K into S. What is S here? So from the figure, you can see S is F into FH. The distance FH is S. So if you substitute that value here, you will be getting the seepage rate through the body of the earth dam. Q is equal to K
Yes. This is the very simple expression to find the discharge Q in terms of the focal distance. Yes. The distance S can be determined either graphically or also can be calculated analytically by considering the coordinates of the point C. So you have at C, the value of X will be equal to D and the value of Y is equal to H. So in the figure, you can see here D and H. So at this point C, this is the value of H. And value of Y will be equal to H. Maximum it can become Y. Maximum it can become H. Similarly, X can take a maximum value as D. So taking H and D, taking H and D in place of X and Y, substituting in this equation, you have S will be equal to, the focal distance will be equal to square root of D square plus H square minus D. So Q is equal to K into S. So substitute that, the value of S here, you get the discharge. So analytically, you'll be able to find the discharge without graphical method also. You'll be able to find the discharge of the seepage rate through the body of the earth dam. So let us work out one or two problems relating to this. For a homogeneous earth dam, 52 meters high, 2 meters freeboard, a flow net was constructed and the following results were obtained. Number of potential drops 25 ND. Number of flow channels NFR 4. The dam has a horizontal filter of 40 meters length of its downstream end. Calculate the discharge per meter length of the dam if the value of K is 3 into 10 to the power minus 3 centimeters per second. So the discharge Q is equal to KH into NF by ND. NF is the depth of water, H is the depth of water, head causing flow. Head causing flow. It is given in the problem, height of the dam is 52 meters, of which 2 meters is the freeboard. 52 meters, height of the dam, 2 meters freeboard. So the head causing flow H would be equal to 50 meters. NF is 4, ND is 25. So K will be equal to 3 into 10 to the power minus 3 centimeters per second given in the problem. That means 3 into 10 to the power minus 3 into 10 to the power minus 2 meter per second. So substituting this value here, K, H, NF and ND, you are getting the discharge. So Q, the rate of seepage through the earth dam will be equal to 0.00024 meter cube per meter length, cubic per meter length. The second problem is, for an earth dam of homogeneous section with a horizontal filter, draw a phreatic line. If the permeability K 5 into 10 to the power minus 4 centimeter per second, also find the seepage flow per unit length. So this is the dam section given more clear. This is the dam section which I have shown at the beginning of our today's class. So I told that do not consider these numerical values there. Okay, so just to understand how the shape of the earth dam with upstream and downstream slope, location of the filter, etc., the same sketch I have copied there and tried to show to you. So this is in a part of a problem. The section is given with a top width of 6 meters, height of the dam is 20 meters here, and you have the base width of this earth dam 146 meters. There is a filter of 30 meters from the downstream toe. So the point F is at a distance of 30 meters from the toe of the dam. This is the location of F. And upstream you have 4:1 side slopes, and the downstream you have 3:1 side slopes. And you need to consider, what to do in this problem? You need to draw the phreatic line. How it flows. That means you need to give certain coordinates so that you'll be able to have a free sketch or a smooth curve to depict the phreatic line from this earth dam section. The other value that is given is K is equal to 5 into 10 to the power minus 4 centimeter per second. Also, you need to find the seepage through this dam. Height of the dam is 20 meters. Height of the dam is 20 meters. And the upstream slope is 4:1. Downstream slope is 3:1. And 6 meters is the top width. Okay, so the top flow line, which is a parabola, can either be drawn graphically or by calculation of its ordinates. So taking F as the origin, the equation of the parabola already we have seen, square root of x square plus y square must be equal to x plus s, whereas c is the distance of the directrix focal distance from the origin of xy or the coordinates of any point on the parabola. xy, p, xy, that is the point that we have considered. So these are the coordinates of any point, and s is the distance of the directrix. So the parabola cuts the reservoir water surface at B such that you have point 146 minus 30 plus minus 30 minus 72. we will see where is the location of this D from the figure. From the figure, the location of the D. First of all, what you need to do? You have to go for 0.3 L. So what is this L? The L is this section, which is given here as 72 meters. So 0.3 L will be 21.6. So you got the point C. You got the point C. Point B is here, and you got point C here. Okay. So this C is the starting point of the parabola, and F is the focus of this parabola. So you need to identify where is the value of D. You need to identify where is the value of D. The value of D will be somewhere here on the filter. So to get this point D, on this your total of 146 meters. And from this 146 meters, this is 72 meters, and this is 6 meters which has to be taken. And you have to identify the point D. Okay, so FB dash will be 146 minus 30 minus 72 plus 21.6. So you have got 65.6 meters. So this value will be square root of x square plus y square minus D, or D square plus h square minus 65.6. Y will be equal to square root of 2x plus s square. For different values of y, you can get the values of x in a small table, like with x is equal to 0, with x is equal to 10, 20, 30, 40, 50, 60, maximum up to 65.6. As you have seen, x can take a maximum of 65.6. So you can find the values of y. So once x, y are known, a smooth curve will provide you the parabola. So the top flow line can be drawn with this, and correction should be applied at the entry and the exit. The seepage flow Q is equal to K into S. K, the value of K is given, and S is the focal distance. We have seen 2.42. Substituting that, you are getting the seepage rate of